Welcome back to another episode of Game Theory. So today we're still in Chapter 12, looking at evolutionary games. Last time I looked at the group project game as a prisoner's dilemma. We're going to do that again, but now add another dimension, and that is repetition. So we saw in the one-shot game that the lazy types were always better than the R types, so there was no stable equilibrium with responsible types. So now let's say our group project game is played twice. So we may have a midterm group project, and you also have a final group project. So we'll still have L types who are always going to be lazy and they don't do the work. They always try to free ride off their partners. And now add a new character to our story. Instead of having R types who are always working, let's have T types. So the T types short for tit for tat. Now tit for tat is one of those strategies that has very little grounding in actual theory of games, but seems to work out often in practice. So here's how it works. What they're going to do is in the first round of the game, they're going to work. And then the second round, they will either reward you or punish you depending upon if you cooperate. So I'll put 2x here for played twice. So if you also do the work in the group project, they're going to reward you by working in the second round. Oops. That's not how you spell cooperate, folks. On the other hand, if you just slack off because you're a lazy type, they're going to punish you by also slacking off in round 2, so that's going to drag down your fitness or your payoff. So where the name comes from, what the tit for tat type does, a T type, is they always play the same strategy that you had played in the previous round. So maybe on the midterm project, you just go play video games while your partner does all the work. You still got good grade because they put in the hours. Can't get away with that again in the final. That's how this tit for tat type works. They like getting good grades, but they also place some value on cooperation and loyalty, and they don't like being exploited. So let's figure out what this is going to look like when they play the game twice. So here's the game. So use W for work and DW for don't work. So if you both work, let's say that's -1. If you work and your partner does not, they get a good grade without putting in any effort, but you did a ton of work, so you don't like that. And it's symmetric. And fine, if you both don't do the work, you both get -12, a bad payoff. So we gotta find out what the payoffs / fitness will be when these types play the game twice. So let's start with the easy case. Let's say you have an L-type paired with another L-type. We said the L-types always play don't work. So they're going to play don't work in the first round, and then in the second round they play don't work again. So LP -12 plus -12. So that's going to be their fitness if we have two L-types paired together on this group project. Now what happens if we have two T-types facing off? We said our T-types are going to work in round 1. So it's T versus T, they both work. Now we also said that if you cooperate with a T-type, if you work in round 1, they're going to reward you by working in round 2. So because they cooperate in the first round, they're going to cooperate again in the second round. Potential objection. Now we know from economic game theory that if you somehow got cooperation in round 1, which you would not get, but if you somehow got it, best response would be to not cooperate in round 2, because after round 2, the game ends, they can't punish you anymore. But here, however, we're not looking at people making choices to maximize payoffs. We're talking about, in biology, people just following what their genes dispose them to do. These guys have it in their genes to be cooperative. So even though, from an economic standpoint of maximizing your payoff, it doesn't make sense to cooperate twice, but if that's what your genes make you do, that's what you do from a biology perspective. So what happens to the payoffs / fitness? They both work in round 1, so they're both getting -1 in round 1. Then they both work again in round 2. They said they cooperate to reward each other for cooperating in round 1, so they both work again, and they both get -1 again. So a T-type is another T-type that can sustain cooperation. So now we have the last possibility. What if you have an L-type paired with a T-type and they're working on the same group project? So we know L-type doesn't work. They just don't do that based on their genes. Now a T-type, we said they always start out by cooperating in round 1. They always work in round 1. Importantly, though, the T-type doesn't know, at least initially, what kind of partner they have. Just like you can't tell just by looking at someone if they're going to be hardworking or lazy. So they always work in round one, so they can't distinguish between L-types and T-types initially. So that means that in round one, our lazy type plays DW, don't work. T-type plays work. That means our lazy type gets a 0 in round one, but our T-type is getting minus 20. Now let's figure out what happens in round two. So L-type is still not going to work because L-types never work. Now T-type, we said, if you don't cooperate, if you don't work in round one, they punish you by not working in round two. So now they're both playing don't work. So when they both play don't work, they both get the negative 12. So that's what happens in round two. Let's put all that together. So in round two, if you have L versus T, they're both getting negative 12. In round one, the L-type got a 0 because it got the free ride. The T-type got a negative 20. So L-type gets 0 plus negative 12, which is minus 12 in total. And our T-type gets a minus 20 in round one because they got exploited. They got to do all the work. And then in round two, they get the minus 12. So our T-type gets minus 32. So that's how we determine the fitness when this game is played twice between these two types of students. Now let's go construct a table that reflects all this. So here's our L-type, and here's our T-type. So we said if you have an L against a T, it should be over here, the L-type gets the minus 12, and the T-type gets minus 32. It's symmetric, so here you have a T against an L. The T gets the minus 32. T gets minus 32. L gets the minus 12. And we established earlier, you have a T against a T. They both work in both rounds, so they're both getting minus 2. So here's T against T. And we also established that if you have an L against an L, they both don't work in both rounds, so they're both getting a total of negative 24. So LL is over here, minus 24, minus 24. All right, so that's how we put this into a table. Let's say that fraction PT are T-types, and 1 minus PT are L-types. Here's a tip about notation. So I could just say P is probably a T-types, but I prefer right now as PT. The reason is that if I see letter P, I'm not sure, is that fraction of T-types or is that fraction of L-types? If I see PT, that's a hint that, oh, fraction of T-types. So I'm doing a little bit more work to write out PT instead of just P, but I like it because it's just a lot clearer that way. If you're confident you're not going to get mixed up, you don't have to put the T in there. You just write P is probably a T-types and you're fine. But if you want to be careful and make sure you don't confuse yourself, I recommend put that subscript in there. So we have a three-step process to analyze this game from an evolutionary perspective. So the first step is you want to find the expected fitness of each type, or in economic game theory, you're trying to find the expected payoff from each strategy. So what is the expected fitness of an L-type? So L-types are in this first row of our table. So with probability 1 minus PT, our L-type is going to be paired with another L-type. When that happens, they get minus 24. So take that payoff slash fitness and multiply it by the probability, and you get this. The other possibility is that our L-type in this row is going to meet a T-type. When that happens, the L-type gets a fitness of negative 12. Backers are probably PT. So let's simplify. So I'll distribute to the minus 24. That's minus 24 plus 24 PT. And then we have a minus 12 PT over here. So that comes out to, if you combine these guys, minus 24 plus 12 times PT. All right, so you found the fitness of the lazy type, or in terms you're more familiar with, you found the expected payoff from plane L. Now let's find the expected fitness of the T-type. So our T-type is down here in the second row. With probability 1 minus PT, they're paired against an L-type, which means our T-type gets a fitness or payoff of minus 32. So our T-type got exploited in round 1 because they did all the work, and then in round 2, they punish their opponent by also not working. So you weight that by the probability of it occurring. The probability is 1 minus PT. Alternatively, the T-type could meet another T-type. In that case, we're over here, and they both get minus 2. And that occurs with probability PT. So I'll simplify. This will be a minus 32. This will be a plus 32 PT. And we still have a minus 2 PT. Then if you combine these guys, that'll be a plus 30 PT. All right, we've done step 1. We now know each type's expected fitness. In the terms you're more familiar with, you found the expected payoff from each of these 2 strategies. Now you move on to the second step of the process. So now what we're going to do is find the mixed strategy equilibrium, or the polymorphism, to borrow the biology term. So we're trying to find for what level of PT are both types equally fit. So that means we have to set minus 24 plus 12 PT. We said that was the fitness of the L types, equal to minus 32 plus 30 PT, the fitness of the T types. So let's do some rearranging. I'll push that 32 over here. 32 minus 24 is going to be positive 8. And I'll move the 12 PT over here. 30 minus 12 is going to be 18. So we divide both sides by 18. 8 over 18 equals PT. That's going to simplify to 4/9. So that's our polymorphism. In the terms you're more familiar with, you call that the mixed strategy Nash equilibrium. Step 3, let's analyze stability. So we look at the stability of the polymorphism, that is the mixed strategy equilibrium, and also the monomorphism, that is the equilibrium where everyone's the same type. So that gives us a total of 3 equilibria. We could have everyone be a T-type. That means PT is 1. We could have everyone be an L-type. That corresponds to PT is 0. And we also have this polymorphism where some are T-types and some are L-types. We analyze stability by drawing the graph of the fitness levels. So F for fitness, analogous to payoff from economic game theory. And PT is proportion of t-types, which cannot exceed 1. All right, so for the t-types, expected fitness level is minus 32, something way down here, plus 30 PT. So it looks like this. For the L types, we said back here that expected fitness is minus 24 plus 12 PT. So it's going to have a higher intercept. The slope, however, is going to be shallow. It'll be plus 12 for the L types rather than plus 30. So it's not quite so steep. So here's the graph for the L types in blue and T types here in pencil. So where are they equal? Well, we just established back here that fitness levels are equal when PT is 4/9. So that's our graph. Now we can analyze stability. So let's say PT is over here somewhere. So it's above 4/9 but less than 1. What's going on over there? Well, at this point over here, you can see that the T types are fitter than the L types. So here T-types are fitter. What that means is that the T-types will be able to survive more, they'll pass in their genes more, and you'll see even more T-types in the future. So that means that PT is going to rise. So if you're in this region here, PT is going to go up. So I'll draw the arrows, bringing us to higher and higher values of PT. Now let's look at this other region of our graph. What if PT is somewhere in here? It's bigger than 0, but it's less than 4/9. By the way, there's some intuition for what's going on here. What's happening when you have lots and lots of T-types in your population? Well, they're going to cooperate with each other a lot. So with lots of T-types, then there'll be lots of cooperation. So T-types are going to benefit from that, and that's going to make them more fit. The L-types are rare, so most of the time the L-types are going to get punished for not working, and that's going to make them less fit. All right, with that out of the way, let's go back to looking at this region of our graph. So if PT is somewhere in here, in this region, you can see that the L-types are now fitter. So if there are lots and lots of L-types in the population, then the T-types are going to try to cooperate. That's their nature, but most of the time, they just get exploited, where the alt type doesn't work no matter what. So most of the time, a T type just gets exploited in round 1, and then that's going to make them worse off. So the L types they'll reproduce more and survive more. So that means there'll be an increase in the future of how many L types you see in the school. So that means that PT, the proportion of T types, is going down. Now, it was either an L type or a T type. So you're seeing more L types, that's going to decrease the amount of T types. So if PT is going to fall in this region, then PT is going to start getting closer to 0 if you're over there. So now the arrows go in the other direction. So that's the dynamics. Now let's talk about stability. We had those 3 equilibria: all T types, all L types, and a little bit of both. If you're all T types, that equilibrium is over here. What happens if you fall a little bit below that equilibrium? So you go from here to over there. Well, now you just follow the arrows. The arrows indicate that if you fall a little bit below equilibrium, the arrow is going to push you back towards that equilibrium. So PT equals 1 is going to be stable. All right, the other monomorphism, that is where all individuals of the same type, that's PT0, which means all L types. So that's over here on our graph. So if you rise a little bit above that equilibrium, if you go from there to, say, somewhere over here, the arrows are going to push you back towards PT equals 0. That's also stable. We have one last equilibrium to look at, folks. That is PT equals 4/9. This one here right in the middle. Well, not right in the middle, but pretty close to the middle, I should say, more precisely. What's going on there? So we start in that equilibrium, and we rise a little bit above it. What happens? Well, the arrows here are going to push us away from that equilibrium. They're going to take us in this direction. So we're not going back where we started. That's going to be unstable. So that's sufficient to prove that PT 4/9 is unstable. You could also check the other direction. You can see that if PT were to fall a little bit below 4/9, you go in this direction here, again, the arrows are going to carry you further and further away towards pt equals 0. So in general, if it's unstable in one direction, then we just call it unstable overall. So what we established is that PT equals 1 in ESS, evolutionary stable strategy. So is PT equals 0. And our polymorphism PT equals 4/9. That's not an ESS. So it still counts as an equilibrium, just not a stable equilibrium. So another big analogy you make here between biology and economics. In general, every ESS is also going to be a Nash equilibrium. However, not every Nash equilibrium is going to be an ESS. So you got to look at this game from an economics perspective. You could verify that PT equals 4/9 is going to be a mixed strategy Nash equilibrium. So it is a Nash equilibrium, but we showed here it's not an ESS. So let's go look very briefly at the Nash equilibria of this game. So let's go back to thinking we're economists and people are choosing the strategy that's going to maximize their payoff. If you're the role player and you're facing L, what's your best response? You want to also play L. So I get minus 24 instead of getting minus 32. If you're the role player and the con player is playing T, what's your best response? You want to also play T, so I get minus 2 instead of getting minus 12. Let's go in the other direction. If our road player is picking L, what does our con player want to do? They could play L and get minus 24. They could play T and get minus 32. Well, it's better to play that and get negative 24. If Rho is playing T, then column's best response, also T. Because it's better to get minus 2 than get minus 12. So those are our two pure strategy Nash equilibria, LL and TT, which correspond to PT is 0 because if there are no T tests, it means L is always played, and PT equals 1. So both are stable strategies. We're also Nash equilibria. But one of our Nash equilibria, the mixed strategy one, with PT being 4/9, was not stable. So again, you can see, even though economists and biologists took some very different approaches to thinking about game theory, the end result we came up with is remarkably similar. That wraps up this section. Come back and join us for our next episode, and we'll learn more about evolutionary games.